Hello everyone, welcome to the presentation on EV ADAS system, a real-time electric vehicle dashboard. Today, I'll be walking through the architecture, code implementations, and final visualization of the system. Let us start with the problem. Modern electric vehicles generate enormous volumes of real-time sensor data, including speed, battery, state of charge, motor torque, and range. With centralized dashboard, it is impossible to monitor EV performance ADAS safety data simultaneously. If an operator tracks these manually, critical events like collisions and blind spots could be easily go undetected. So, solution. To solve this, I have implemented the central EV ADAS dashboard system, which provides the solution providing the real-time monitoring of the speed, SOC range alongside ADAS collision and blind spot detection. It features a tiered alarm system, live telemetry via UART, and dynamic Python dashboard. For the tech stack, I have used STM32 Blue Pill microcontroller. Because we need a safe environment to test the firmware, I have used PICSimLab simulator, which maps virtually potentiometers and ultrasonic sensors to STM32 pins. Then this is sent through serial port via UART to Python dashboard. Now let us move to the demonstration phase of the project. As you can see on my screen layout, you can completely see the connections I have made using STM32 and the potentiometers and ultrasonic sensors. Here the potentiometer one states acceleration, second potentiometer is brake pedal, and third potentiometer is state of charge, and fourth potentiometer is motor temperature. And the three ultrasonic sensors detects as the front distance, left distance, right distance. Here we can see four fault LEDs which detects the collision, left brake, left blind spot, right blind spot, and fault. And this is virtual terminal where you can observe the output of the implementation. Here you can observe the speed, SOC, torque, temperature, range, acceleration, brake. FLR are front distance, left distance, right distance, time to collision, collision warnings, blind spot detection, alarm, and faults. You can use this reset button to reset the data and you will start new data. The acceleration is positive and the brake is zero, hence you can observe the torque is positive. Here you can observe that as the speed increases, the state of charge decreases and torque increases. If we increase the brake and decrease the acceleration, you can observe that torque has been reduced and it is in negative. Hence, we can say that we successfully implemented the car system of it. This is STM32 where I have implemented the coding part of this project. Here in the EV dash, we can observe the ADAS file, EV control file, fault file, and a UART file, and ultrasonic file. In ultrasonic file, we define the ultrasonic distances and then its maximum limits. In UART file, the data to be transferred and the baud limits are defined. This is the main file where everything of the every other file has been called. EV control, ADAS, fault, UART shell, common. In this, all the fault states have been marked, and all the LEDs that blink comes from this file. In the EV control file, you can observe the state, park, state ready, and the driving state of the car. This is ADAS file where the ultrasonic sensors has been defined and their maximum distances and the left blind spot, right blind spot, and everything else of the ADAS system has been defined. This is the basic setup of the project, and we open the PICSimLab and open the file which we have created from the STM32 cube ID. This is ev-bin file, and this has been loaded. After it, we can select the module, spare parts, and the potentiometers, and everything has been loaded. Here we can observe that the state of charge at start was 97, around 100%, and the acceleration and motor was 0, like the speed is 0. As we increase the acceleration, the speed also increases relatively, and the torque also increases. If we increase the brake, the torque decreases, and also the speed decreases. If we decrease the front distance, we can observe that the collision warning has been called off. Since the basic structure of the project is done, we can then emulate it using VSP. VSP is the virtual serial port enabler, where the serial ports are connected using virtually. Like here, I have connected the COM1 port with COM2 port, where COM1 port is the input and the COM2 port is the output. Since the COM1 and COM2 ports are connected, we can check the data using TeraTem5. Here we select the serial port and the output. Our output port is COM2 port, so we select the output port. Here we can observe that all the data that has been transferred via UART is traveling from COM1 port to COM2 port via UART. We can observe the initial SOC data and all. We can check whether the data is correct or not by using this. Like if we decrease the brake pedal, we can observe the speed increasing and SOC decreasing. Since we are receiving the data through COM port, we can start implementing on the Python dashboard. This is EV ADAS dashboard that I have been implemented using Python. This is the Python script which I have been using to implement the ADAS dashboard. Now let us look at the Python dashboard. This is the speedometer and this is the speed history, and here we can see the EV metrics, and this is the range, and this is the battery SOC. This is the ADAS bird eye view where the ultrasonic detects the front car left collision and right collision. Now let us see the output of this. Here we take the sensors of the EV metrics, and if we the first potentiometer is accelerator. If we increase the acceleration, we can observe that speed has been increasing rapidly, and we can observe the acceleration as at 86%. In the same way, if we increase the brake, we can observe the torque has been decreased and the brake percentage has been decreased. Torque has been negative, and the battery starts charging. We can observe that battery health has been increasing because this is because due to regenerative braking. And if we decrease the front distance of the car, we can observe that in the ADAS bird eye view, the front distance decreased and the time to collision also decreased. If we decrease further more, we can observe a critical error known as collision error. In the same way, we can also decrease the left and right collision of the cars. As we decrease furthermore, we can observe that left and right collisions has been occurring. And that's the project. Moving on to the hardware mapping. We mapped pins PA0 and PA1 to the ADC1 peripheral and PA3 to the ADC1 input, and HCSR04 to PB0 and PB1. PA9 and PA10 are connected to the USART pin. Finally, moving to the sensor configuration, we have used 3 ultrasonic sensors, one for fadent detection, one for left blind spot, one for right blind spot. The front server monitors 0 to 4 meters, while left and right monitors up to 30 centimeters. After that, we have implemented the speed using a simplified Euler integration model, where we used velocity-dependent drag coefficient to calculate the net acceleration. We also monitored energy by using torque and speed. We then add motor copper losses and integrate total power drawn over time to accurately decrement the battery state of charge. To mirror rear-road EVs, we implemented adjustable drive modes and energy recovery. Drivers can select between Eco that grabs maximum throttle at 60%, normal at 100%, and sport at a torque of 130%. Additionally, our regenerative braking system activates when the brake pedal is more than 5%, which decreases the torque and increases the battery percentage. Our primary safety net is forward collision system, where we calculate the time to collision of the front body, and the system drops a warning state when the time to collision drops below 3 seconds, or the absolute distance falls below 50 centimeters. It escalates into critical states when it escalates below 50 centimeters. For lateral safety, our blind spot detection actively monitors adjacent lanes to prevent annoying false positive low speed maneuvers like parking. This logic is strictly gated and only activates when the vehicle is traveling about 20 kilometers per hour. If an obstacle is detected in this zone, it is triggered as level 1 advisory state. We have also implemented the fault management logic to handle critical safety states. If the motor temperature exceeds via PA3 90 degrees Celsius, the system triggers fault 0T and instantly cuts the motor PWM to prevent overheating. If the SOC integration model dips below 2%, fault SOC is raised to prevent the damage of the battery. If ADAS system escalates to critical level 2 warning, fault collision forces emergency software to avoid collision. To get this data to the engineer, we rely on a robust UART telemetry protocol. We transmit the structured strings containing data points like speed, SOC, torque, temperature, and sensor ranges at 1,15,200 bps. The data stream is decoupled into 10 heads and 1 head streaming rates to optimize bandwidth and parsing. We also built a custom interactive UART shell for testing and control. It uses non-blocking input-output built-on customized ring buffer driven by UART RX input, which prevents CPU stalls. This allows engineers to use parameter injection like forcing the speed to 80 or temperature to 95 to validate UI behavior without needing any physical hardware triggers. You can also run fault simulator commands like fault injection motor to determine the trigger priority alarms, and then use the fault clear command to safely reset the state machine back to state park. All of this telemetry drives our central Python dashboard. The visual interface relied on Matplotlib backending using utilization function animation to draw custom UI widgets at smooth 10 frames per second. The incoming telemetry is passed using regex in a dedicated background threading loop, keeping the main UI thread highly responsive. For presentations like this, we also included a synthesis demo mode that bypasses the serial port and generates physics-accurate sine waves to simulate traffic overtaking and battery drain. The dashboard itself is broken into three main visual elements. First, the arc speedometer with dynamic green to red color scaling based on speed, along with the historical 60 sampling roll line chart. Second, our energy metric section where where it features a horizontal SOC bar chart displaying live battery percentages, estimated range in kilometers, and then current drive mode. Finally, the bird eye view offers a top-down lane rendering the generate visuals arcs of our TTC color coding leading obstacles and highlights the lateral blind spots. I also, during development, we made a critical implementation modifications. First, we resolved buffer caching issues by replacing the blocked standard scanf function with scanf in UART shell seed, allowing firmware to process the serial link buffer string reliably. Secondly, we fixed an aggressive override our state machine routing with a fault C. Instead of automatically forcing the car back to state driving after a fault recovery, it now safely holds a vehicle in state park. Under the hood, timing is crucial, and we utilize three main hardware timers. Timer 1 operates at 100 Hz, running a 10 millisecond interrupt to handle the EV physics loop, IDC polling, and speed SOC integration. Timer 2 acts as 1 microsecond resolution counter to provide precise blocking delays for the ultrasonic trigger and echo pulses. Timer 3 operates at 10 Hz, providing 100 millisecond interrupt for ADAS engine trick, which triggers the sequential routes of HCSO04 sensors. Sensor system reliability, we underwent strict testing and validation. We have verified bidirectional UART command integrity using virtual serial port emulator prior physical development. We tested sensor edge cases by utilizing the PICSimLab sliders to simulate erratic obstacle appearances, which validated ADAS heuristic logic and debound counters. Lastly, we confirmed safe environment by verifying the PW motor torque output successfully drops to 0 nanometers during injected critical and SOC faults. To wrap up, I want to take a brief moment that reflect my time during this Emertxe Embedded Internship. Building this EV ADAS system has been an incredible practical learning experience. I gained hands-on expertise writing STM32 firmware, implementing real-time safely algorithms, and bridging the embedded hardware with a Python-based telemetry dashboard. None of this would have been possible without the continuous support and guidance of Jayalakshmi ma'am.